the first type of probability for a compound event is where I'm going to look at two events happening, and I want to know the probability of both of them happening. You already did some of these the other day on that little check worksheet that I gave you on Friday, the one with the spinners and the pictures of the die and that kind of stuff. So if I say I want to know the probability of two things happening, normally, what operation do we do between the two? So for example, I say you're going to flip a coin, Sydney, and I want to know the probability of you flipping a coin and getting heads.
50%.
Okay, so how would you express it as a fraction? Okay. Now I say you're going to roll a die. I want to know the probability of you getting a 4.
How many numbers are 6? 4 over 6 reduces to 2 over 3. Right?
What? There's only one form of the die, but every
I
time.
don't know. See, this is why I don't talk in this class.
That's actually not true. You talk a lot.
1 6. Not out loud. 1 6.
1 6 because there's 1 4 out of 6. So if I say I want to know the probability, if that's your experiment, you're going to do both those things. You're going to flip a coin, and then you're going to roll the die. You did some of these the other day. And I say probability of you getting the heads and you getting the 4. What would you do with your 1/2 and your 1 out of 6? Probability of heads.
I was supposed to write this down.
And probability, that's up to you, I guess. I would.
Don't look at me like this.
Probability of the number 4 on a die. You said they were 1/2 and 1/6. If I want to know the probability of both of those things occurring,
I thought this was going to be definition, that's why I asked.
what would be the overall probability that both of those things will occur? How did you get that? Okay. You guys did that for me the other day. 1/2 times, so we multiply those together. 1/6 gives me 1/12. Those two events that I described to you are what we call independent events, because they're events that are happening independent of each other. I know we use that word in math otherwise. So when I say independent, I'm talking about events that don't affect one another. Okay. As opposed to if I were to have dependent events where one's probability actually affects the next one's probability. So an example of this one is heads and the 4, because those two things don't happen to affect each other. Another way I could do this would be thinking about pulling cards out of a deck independently. I could say, what is the probability of me pulling a 4 out of the deck?
Any 4?
Putting it back into the deck, and then pulling another 4. They're independent. Why?
Because it doesn't matter what the first one was, because it's the same probability.
You don't depend on the answer to change.
Right, the answers aren't going to change. Same thing here, heads and then the 4. They're not going to affect each other. Can you think of a situation for me, though, where that's not true?
You draw the card, you don't put it back.
Okay, I draw a card and I don't put it back. So events change the future probabilities. The events don't change. So you said an example was, I draw a card and I don't put it back. So let's say that it was that probability of me pulling a 4 in a deck of cards. So let's say this is a deck of cards. What's the probability of me pulling a 4?
4 over 52, 1 over 13.
Okay, 4 out of 52 or 1 out of 13. Now if I'm not putting the card back, what is the probability of me then getting another 4?
3 over 51.
Good. I could multiply them together. And I would get 12 out of, can't do that other one in my head. I'm gonna need your guys' help. Sydney's doing it. Wait for her.
265.
You grabbed it right to do the calculation for us?
Yes, I did.
Yeah, what is it? Thank you. Can we reduce that? I know I can because they both ends in 2s.
265 divided by 2.
1 over 221.
Ooh, it even goes divided by 12. What was it? 1 over,
221.
thank you. How would that probability be affected if we did put the card back?
It'd be 4 over 53 times 4 over 52. So there'd be a higher chance of it.
A higher chance of it happening?
It would be higher.
I would have 4 over 52 and then I'd have 4 over 52 again. So I'd have 16 over something.
16 over like 2800. No. 2704.
Does 740 and then 16.
The probability higher or lower? It's hard to compare fractions, so one thing you could do is compare decimals. If you looked at 1 over, what is it?
1 over 169.
For the other one?
It would be lower. It would be higher chance.
Higher.
1 over 169.
He said for the other one, if this situation would have been independent, so replacing cards, sorry, I'm running out of room, you might not want to write this, but replacing cards, if I did the probability of a 4 and then another 4, you said it'd be 1 over 169. Final answer? That was 16 divided by 52 times 52? Okay. So which one's the higher one?
Independent. No. Yeah. It's the independent.
Because it's a smaller denominator, so 1 out of a smaller amount would be a larger amount. Or if you wanted to check, if you're not sure, you could always divide and get a decimal. Think about percentages. Think about them. But it's true. So your probability is lower when you don't put the cards back. Why? Because there's less 4s to pick from compared to the amount of other cards. So we're going to look at some more of these today. The only thing that's going to change is that sometimes they're going to be dependent events where you'll have to pay attention to how one probability affects the other. Okay? I think you've already thought about this type of probability before. This is the type that I don't know that everyone has thought about before, though. Probabilities with the word or in there. So I'm going to ask you to look at a few problems in a second that have the word or in the problem. Rather than me saying I want you to get a 4 and another 4, I might say I want you to get this thing or this thing. So think about something really, really simple in terms of cards. Let's say I said I want to find the probability of you drawing a card out of a deck, and I wanted to know the probability that that thing was either a 2 or a 6 out of a deck of cards. A 2 or a 6. So deck of cards. I want to know the probability that you pull a 2 or a 6. How would you figure that out? How many
8 over
cards would you be successful with?
8 over 52.
8 cards would make me happy
13.
out of 52. Why 8?
Because there's 4 2s and 4 6s.
4 2s would make me happy, and 4 6s would make me happy. Each of those coming out of 52. Now, why did I write them separately? Just to help you think about what you just did. You added together the total number for the 2s with the total number for the 6s to say that there are a total of 8 cards that would make me happy out of 52, and then we could reduce. Can someone do it for us quick?
2 of 13.
I just don't like leaving them not reduced. Okay. This is what we call a mutually exclusive event. I want you to think about how you would change your math for my next problem. My next one's going to be a very similar one, but it's going to be what we call mutually inclusive. In my same deck of cards, I want the probability of you pulling a 2 or a spade.
So let's see,
How many spades are there?
there's a 13 over 52 chance of getting a spade. There's
Okay.
3
So
over
how many
52.
cards would you be happy with out of that deck? Total number of successful cards that are either a 2
Eight,
or a
66.
spade.
60. 60.
How do you get there?
There's 13 spades.
There's 13 spades, so I'd be happy with any of
And
them.
there's 4 twos, but one of the twos is a spade, so that only counts as 1. So 13 plus 3 is 16.
What do you guys think? If I was naming the cards, I'm happy with the 2 of spades, the 3 of spades, the 4 of spades, the 5 of spades, the 6 of spades, 7 of spades, 8 of spades, 9 of spades, 10 of spades, Jack, Queen, King, and Ace of spades. Those were his 13 cards he named. But then he said, in terms of other cards, I'm also happy with the 2 of diamonds, the 2 of hearts, and
2 clubs.
the 2 of clubs. I don't recount the 2 of spades because I already counted it. So in terms of your math, you think about your 2s, you're happy with 4 of them. You add in your spades, there are 13 of them.
Well, at that point, it's only 12.
What's that?
At that point, there's only 12 because you're already counting the 2 spades.
So I have to get rid of the double counted spade. You could either do 3 out of 52 and then 13 over 52, or you could do 4 over 52 and then add 12 over 52. The question is, you got to make sure you don't double count something. So that's why mathematically the way that they'll write the formula to this is they'll say add them both together and then subtract. All of those are the same math. So honestly, in terms of the work you show, you could do either one. This is nice because it helps people think about the double counting and they don't have to worry about forgetting to take it out, you know. But if you take it out on your own, you're fine. The way the formula is written is they'll say find the probability of A, add in the probability of B with the 2s being A and the B's being spades. So add them together and then subtract all the places where they overlap, where you're an A and a B, because we don't want to double count. That's what the formula will say when you see it, when you're actually studying stats. But yeah, all of that math does the same thing. We should get a total of 16 over 52. And we could reduce that and get 4. Thanks. So how would you describe to somebody the difference between a mutually exclusive event and a mutually inclusive?
One of them is a lot, one of them is not a lot.
The mutual exclusive, you have to separate the two and then probabilities. And then the inclusive, it's all one thing.
What do you mean by one thing?
Like the two probabilities are one.
Some of them are. Yeah, you want to add to that, Nick?
No,
You like his explanation?
In exclusive, the 2 items.
Oh,
In exclusive, the 2 items are the same, or more than 2 items are the same. And inclusive, they're of different types.
other way around though, what you said. Exclusive, they are different types. Inclusive,
That's what I said. Exclusive are the same thing. Because they're all numbers rather than numbers and series.
oh, yes, in this problem, but would it always have to be that they're all of the same thing? Like, could I come up with a situation where they're maybe not all numbers, but they're still exclusive of each other? Like, for example, flipping the coin and rolling the die, would those be exclusive or inclusive?
Those would be
They would be exclusive because I couldn't have the same thing happening at the same time, basically. This one, there is some sort of overlap. This one, there's no overlap in your sample space.
Are you saying that you can't put it back?
I'm not really thinking about putting back or not putting back in this situation with the word or. I'm thinking about whether or not there are pieces in my sample space that are getting double counted or not, meaning do they actually overlap? So if I say A and B are the 2 things that I'm taking the probability of, the way I've also seen this drawn is that an exclusive event means like these are all the things that I could get for A, these are all the things I get for B. None of those numbers occur in both of those. But in this one, these are all the things that would make me happy for A, and those are all the things that would make me happy for B, and there is an overlap of something. There's a 2 of spades that falls into both categories. So when I say or, I gotta take out that overlap. I think it's one of those things that starts to make a little more sense as you try some of them. So all I'm going to do today is give you a couple to look at and try and to think through, and we'll see how it goes.